Oops. All right, so this problem that we have here, this is a horizontal circle, but it's actually the first horizontal circle where we are where the force causing the change in direction is the normal force. So you've already seen problems where tension caused the change in direction and where friction caused the change in direction. This problem, actually, the force that's causing the change in direction for the person on this ride is the normal force. So if I draw the picture, which is always the first step in these, I'm going to have the normal force in this direction. And now we make the ride go fast enough. The faster the ride goes, the more this particular force grows. And at some point, there'll be enough normal force to have enough friction so that the person won't slide down the wall. So the other two forces on this problem are going to be the friction and the weight. So we have the weight in this direction, and we have friction in that direction. So in past problems, we've had where the friction was over here and the normal force was over here, but it's a completely different problem. The person's spinning around here, and they're going to be stuck up against the wall, so the wall of the ride keeps them moving in a circular path, and when the floor drops, we don't want them falling, so we want to have enough friction so that it overcomes their weight, so they stay stuck up against the wall. So after you have the picture, the next thing you have to do is write the descriptive equations. So if I sum up my centripetal equation, my centripetal force equation, there's only one force causing the change in direction. So, and it is towards the center of the circle, so it is a positive force. So the normal force is going to equal either mv squared over r or mr omega squared, depending on what the unknown is in the problem. And actually, in this particular problem, the unknown is the radius. So it says, assuming a coefficient of friction of 0.20, what radius should the ride have if we can safely make the floor drop away when it reaches its running speed? So that means that I am going to make the normal force equal to mr omega squared, because r is my unknown. Now, we have, if we look at the other force, and you know, you can't write what I'm writing down now unless you have a picture, because the picture is describing something, and if that something isn't there, then you can't write descriptive equations. So don't memorize things. You should learn this so that it makes sense and you understand it. You shouldn't be memorizing anything in solving these problems. So the normal force in this case is going to be friction minus W equals 0. Because again, we're looking for the minimum. Certainly, I could potentially have more friction than my weight, but I want exactly what I need so that the ride can be, at the running speed, I want these two to be equal. So the next thing is, we know that friction equals mu Fn, and Fn equals mr omega squared. So I'm actually going to do a substitution here. I'm going to replace this with mu mr omega squared. And one thing about these problems is they're sort of clean problems. Like when you're solving them, it's not like if you're doing it right, it shouldn't be like a cluttered problem. Like some of the problems we do, you just have a lot of stuff and things to calculate. Here, it's not very cluttered. So friction, I'm going to replace friction with mu mr omega squared, because what I just wrote there, that's mu Fn, and mu Fn is friction. So friction minus, now if I look at the problem, there's no mass or weight given in the problem. So I'm going to replace the weight with mg. So it's going to be minus mg equals 0. So there's my equation. All I have to do is, now if I divide through by the mass, it cancels out. So the mass cancels, and the mass cancels. And all I have to do now is rearrange the equation to solve for the r, and I'll be done with the problem. So we can see that the r is here. So that means I'm going to move this minus g to the other side, which would make it positive g, and I'm going to divide by the other members of the term. So I'm going to get r is going to equal g divided by mu omega squared. And now I know everything I need to solve. Now, we already have the g, because that's a constant, and we know the mu because it was given as 0.20. So I need to get the omega, and that has to be in radians per second. Right now, the angular velocity is given in revolutions per second. So I am going to have to do a conversion to convert that into radians per second. So that's the next step. Omega is 0.5 revs per second. And I'm going to go from revs to radians. From revs to radians. And in one revolution, how many radians do you move through when you go in one revolution? 2 pi. So there's 2 pi radians in a revolution, and there's 2 pi radii in a revolution if we were converting it into meters. But we're going to radians here. So what do you get when you actually solve that? Omega is going to equal what? Oh, 3 point, yeah, because half of 2 is 1, so it's basically pi. So 3.14 radians per second, and now just plug in and we'll have the answer. So R is going to equal G over mu omega squared. And so for G, we're going to put in 9.8 meters per second squared. For mu, we put in 0.2, right? That was mu. And the omega is 3.14 radians per second. And this is what I mean about the units messing up when you have radian involved in the problem. If you look at the units here, I'm going to get the second squared, we'll cancel the second squared, but I'm going to be left with meter per radian squared, and I'm telling you the answer is meters. Okay, so like just ignore the radian unit. Again, it's like a false unit. It's a unit that allows us to go from something angular to something linear, but I mean that's all it is. So what do you, when you solve this, what do you get? 4.997 or 4.97? 4.97 meters.